Distillations. Background and simple distillations. In this webcast, we will discuss what distillations are and how they work. We will then discuss the distillation you will perform in the unimolecular nucleophilic substitution experiment, a simple distillation. Distillation is a method for the purification of liquids, and the reason it is exclusively for liquids is because it separates compounds based on their boiling points. In a distillation, compounds undergo a series of phase changes. In the most basic of distillations, your liquid will be converted into a gas and then will return to being a liquid, hopefully more pure than when it started. In this particular experiment, you'll be performing what we call a simple distillation. Simple distillations are quick to perform. However, they are only appropriate for mixtures that contain compounds with large differences in boiling points, where large is at least 40 degrees Celsius. During a distillation, you will be recording the boiling point of the liquids as they distill. In the same way that a melting point is characteristic of a compound, the boiling point is also characteristic of a compound. You can use the boiling point of your compound as it distills to try and identify it. The distillation apparatus you will set up in this experiment is the most complex apparatus you will have used in this course so far. This image shows a completely set up distillation apparatus with one exception. Remember to include the metal hose clamps to secure the connections between your hoses and the condenser, which are not shown here. In a distillation, you will place your liquid into this round bottom flask, often called a distillation flask or the distillation pot. The liquid in this round bottom will be heated using this hot plate and the aluminum block until it begins to boil. When it boils, it will be converted into a vapor and travel up the apparatus until it reaches this intersection. At this intersection, we have this metal rod. This metal rod belongs to a thermometer. Your vapor will touch this thermometer, which will allow you to record the temperature of the vapor, which is the same as the boiling point of the liquid. Your vapor, once at this intersection, will then travel down the condenser, hitting the cool walls and condensing back into a liquid, which you will collect here at the end. Before beginning your distillation, you must have your TA check your apparatus. An improperly set up apparatus can become a pressure vessel, which can explode. There will be points associated with your TA checking your apparatus in this experiment. Additionally, you will be using heat, and as always, remember that hot glass looks just like cold glass. Do not touch any part of your apparatus until you know that it is safe to touch. Thus far, we've talked about the practical aspects of a distillation. Now let us discuss how a distillation actually allows you to separate liquids. Let's start with the basics. If a distillation separates liquids based on their boiling points, we should talk about what boiling points are. The boiling point of a liquid is the temperature at which the vapor pressure of the liquid equals the external pressure. Consider a jar that I have poured some water into and then sealed the jar with a cap. The water in that jar will begin to evaporate and form a vapor in the space above the liquid. The pressure of that vapor is the vapor pressure. This graph shows the boiling point of a liquid as the vapor pressure of that liquid changes. On the x-axis we have temperature in degrees Celsius, and on the y-axis we have vapor pressure. Consider a situation where we are at atmospheric pressure 760 torr. When our liquid boils, the vapor pressure must also equal 760 torr. If we want to know at what temperature it boils, we simply look at 760 torr, move over to the right until we encounter this line, and then look to the x-axis to find the boiling point, in this case looking to be about 62 degrees Celsius. Now, let us lower the atmospheric pressure by using, say, a vacuum. If you lower the atmospheric pressure to 380 torr, that means our vapor pressure now has to equal only 380 torr in orr to begin boiling. The new boiling point would be, if we go over to the right until we encounter this line and then look down to the x-axis, about 47 degrees Celsius. The take-home message for this slide is that the higher the pressure of the atmosphere, the higher the vapor pressure needs to be. the higher the vapor pressure needs to be, the higher the boiling point will be, because we need more energy to reach that vapor pressure. This diagram here corresponds to a pure liquid. What if we start adding impurities? If we add a non-volatile impurity, we get a decrease in vapor pressure. That means we need a higher temperature in order to get that liquid to boil. There are many components on this slide. Let's talk about them one by one. A non-volatile impurity is an impurity that has no vapor pressure. In this diagram, sugar dissolved in water would be a non-volatile impurity. Why would adding a non-volatile impurity decrease the vapor pressure? One way to rationalize this is to consider the adding of the impurity as diluting the liquid. You may find it useful to review your notes on general chemistry if you are struggling with that idea. If we lower the vapor pressure, why would that increase the boiling point? Well, remember, a liquid boils when the vapor pressure equals the atmospheric pressure. This red line is the vapor pressure of water as temperature increases. If atmospheric pressure is 760 torr, we have to heat water to 100 degrees Celsius for it to boil. If we add a non-volatile impurity, our vapor pressure decreases. This blue line here shows the vapor pressure of water with our non-volatile impurity. At any given temperature, our vapor pressure is lower than the red line. As a result, the liquid has farther to go to reach 760 torr. We need a higher temperature to reach the same vapor pressure. Now, let us say that instead of using a non-volatile impurity, we use a volatile impurity. For this experiment, let us assume that Raoult's law holds. Raoult's law states that the vapor pressure of an ideal solution is dependent on the vapor pressure of each chemical component and the mole fraction of those components present in the solution. What do I mean by ideal solution? An ideal solution is a solution in which the interaction between like molecules are the same as those between unlike molecules. Consider a solution that is a mixture of A and B. If this is an ideal solution, the AA interactions are the same as the BB interactions, which are the same as the AB interactions. Fortunately for us, many organic solutions approximate the behavior of an ideal solution. Now that we know what an ideal solution is, let's talk more about Raoult's law. Let us consider an ideal binary mixture of A and B. What Raoult's law is saying is that the pressure of component A is equal to the vapor pressure of A if it was pure times its mole fraction. Similarly, the vapor pressure of B in the mixture is equal to its pure vapor pressure times its mole fraction. The total vapor pressure should equal the vapor pressure of A added to the vapor pressure of B. Remember Dalton's law of partial pressures from general chemistry? That's what this is. What these relationships state is that the vapor pressure of a component depends on how much of it there is. The higher the mole fraction of a component, the more its vapor pressure contributes to the total vapor pressure. And the total vapor pressure is equal to the sum of the vapor pressures of the individual components. If we take this mixture of A and B, we can take these relationships and develop a phase diagram. In this phase diagram, we are plotting the temperature in degrees Celsius versus the mole fraction of one of our components, in this case, component A. Mole fraction, our old friend from the two-component phase diagrams from the melting point experiment. All the things we discussed about mole fraction back then still apply here. Make sure you read the x-axis carefully and read any questions carefully for what I'm asking for. In this phase diagram, we have two lines. We have a liquid line down below, and we have a vapor line. The liquid line corresponds to the liquid mixture of A and B. The vapor line corresponds to the vapor we are making by boiling A and B. Make sure you use the correct line for the questions that I will be asking you. To begin interpreting this phase diagram, let's start with a simple question. What is the boiling point of a mixture that is 80% A? To start, let's locate 80% A on the x-axis. Our x-axis is in mole fraction of A, therefore a mixture that is 80% A will have a mole fraction of 0.8 for A, which is right here. To find the boiling point of this mixture, I go up until I hit the liquid line. Once I've hit the liquid line, I then go all the way over to the y-axis to find the boiling point. Here, looking to be about 102 degrees Celsius. Not too difficult. Now let's go deeper into interpreting this phase diagram. When distilling an ideal mixture, the vapor is richer in the lower boiling component. Now note that when I say richer, it doesn't necessarily mean a majority. When I say richer, I mean compared to the liquid. If our mixture contains 30% B, and it is the lower boiling point component, the vapor that is formed from boiling our mixture might be 35% B or 40% B. It depends on the phase diagram. In this particular phase diagram, component B is the lower boiling point component. How do I know that? Let's look at the phase diagram. We see here on the x-axis that we are talking about the mole fraction of A. When I have pure A, a mole fraction of 1, I have a boiling point of about 110 degrees Celsius. In contrast, when I have a mole fraction of A of 0, in other words pure B, I have a boiling point of about 78 degrees Celsius. That means that for this particular mixture, the vapor I form from boiling the mixture should be enriched in B. Let's say I am starting with a mixture that is 80% A and 20% B. Like we had on the previous slide. That means I'm starting here on the right. What is the composition of the vapor being formed? Like before, we are going to go up until we hit the liquid line. To answer this question, we are not going to go to the y-axis. To answer this question, we are going to go until we hit the vapor line. And finally, once we've hit the vapor line, we return to the x-axis, and this here tells us the composition of the vapor, looking to be approximately 58% A and 42% B. Let's talk through that again. I have some starting mixture, 80% A, 20% B, which is here on the x-axis. I go up until I hit the liquid line, and then I go to the left until I hit the vapor line. By returning to the x-axis, I find the composition of the vapor. Notice how my vapor is enriched in B. I've gone from 20% B in the liquid to 42% B in the vapor. Now let's say I take my vapor and condense it and turn it back into a liquid. What's the composition of that liquid? Well, hopefully you find it easy to see that the composition of our collected liquid after the distillation has to be the same as the composition of the vapor, because we are turning the vapor into the liquid we collect. So at the end of the day, what do we have? We have a collected liquid that is enriched in B. But we are nowhere near having pure A or pure B. How useful is this technique really? Well, remember, this technique is only used if there is a significant difference in boiling point, at least 40 degrees, which we do not have in this mixture. For liquids with large differences in boiling point, a simple distillation works quite well. But for liquids with a small difference in boiling point, you have to use more advanced distillation techniques. You will learn one of these, fractional distillation, in the next experiment. That brings us to the end of this webcast. To recap, distillation is a method to purify mixtures of liquid compounds. Separation occurs due to a difference in boiling points. The vapor produced from a distillation of a liquid mixture is always enriched in the lower boiling point component, assuming your mixture is an ideal mixture. A mixture boils when the mixture vapor pressure equals the external pressure. For an ideal solution containing volatile impurities, the vapor pressure is dependent on two things: the pure vapor pressure of each component in the mixture and the mole fraction of each component in the mixture.